So solving quadratic trig equations. Some of these aren't even exactly quadratic trig necessarily. They kind of are. Is quite different. The end of it, like there's going to be a few steps that we do, and then at the end, we'll be solving an equation just like we were doing the last day, right? So the end of it is the same as the solving trig equations that we've already done. So again, hopefully you're good at that as well. Not as often that we change the period. That's the trickiest part about just solving regular trig equations, was changing the period. I was talking to a bunch of people about that today, throughout the day. But quadratic, the challenge, I would say, is different. When you solve quadratic equations, let's take a look at one. Don't write this down. So x squared plus 6x plus 5 equals 0. What makes this a lot trickier to solve than something like this? 2x plus 3 equals 5. Go ahead. Yeah, but not just the square, because I could make a third equation here, x squared plus 7 equals 0. That's not too difficult to solve. And think about how I would solve each of those three in a different way, like different strategy. Right.
It kind of looks as if you were to have like a y and an x there.
Okay. Yeah. How would I solve the blue one, the linear equation? Just isolate. Get x all by itself. That would be easy. I hope that would be easy for us at this point, right, in our math career. How would I solve the red one? Or let me change it to make it. I could solve you could do difference of squares, but I could also solve that by isolating. Isn't that true? Move the 7 over, take the square root of both sides. So, like, there's no rule, and this is why we're doing kind of one day where all of a sudden, all the stuff we know about solving different kinds of equations in different ways comes into play. Like all of it. And that can make it tricky. Think about, so let me show you one last type that I can think of. This 2x squared plus 10x equals 0. Like each one of those has a slightly different sort of style or like outcome of a process of how you're going to solve it. And you're going to need all of these skills and all of this thinking in order to be successful today. So this one would be like, this is a nice example, because what can I do? Well, I can do 2x and then x plus 5 equals 0. And then I use the zero product property, right, to solve the rest of this. Okay? And so in effect, I have isolated for my variable, right? I can isolate x. That was our strategy of using the zero product property, was to isolate your x. Okay? What about this one? Well, I could use quadratic formula, but I would factor it likely, and again use zero product property. Okay? So let's examine these four. We're not going to solve them yet. We're just going to look at them, and we're going to think about how could I, in effect, isolate x for each of these four. X, exactly, x squared minus 2x minus 3. So you're going to factor and get the exact same thing. And I see that in this case because it's sine squared and 2 sine. So I can replace, and sine squared x is like, is the way that we write this, right? So I can replace sine of x with x or a or y, whatever you want, and just factor it like that. But I recognize that as a particular type. What about this one? Why can't I do that for this one? Sharif? Yeah. Right. That would be like 2x squared minus 5y minus 5 equals 0. Well, that you can't just factor that. Think about what factoring is. It's the opposite of expanding. So there's something else going on with this one because of the fact that it's a secant and a tan. They're different. I have to fix that first. Anybody have an idea? Sharif, yeah? Yeah. You could use an identity, secant squared. We have an identity for that, right? There we go. Secant squared is 1 plus tan squared. Now I've got tan squared and tan. I'll have to do a little bit of work to kind of put it in the right order, but that's going to work, okay? And the reason why I knew I had to do that is because I can't factor it with an x and a y, an a and a b. They got to be the same thing. What about this one? I mean, it's similar in that I've got sine x, sine squared x, cos 2x. Like I have all kinds of stuff going on there. So somehow I have to put this in a form that I can factor to get individual parts that are solvable. Anybody have an idea of what I could do here? Justin? We're probably going to want it to be equal to 0. Typically, we're still going to take advantage of the zero product property. So we're going to want the right side to be 0. That would kind of isolate the parts from each other, but it's not going to help us solve ultimately. Very nice. We have an identity that turns cos 2x into sine x, sine squared x. Like it's a bit more complicated again, but ultimately that will give us all sines and sine squareds. And then I can kind of rearrange, get it in the right order, factor or whatever, however it ends up working out. And then question D is different again. So you, in the next few days, have got to familiarize yourself with all the different types. They're slightly different. You need to recognize them. I think that's the challenge of this topic in this unit, is people don't really get and see the different types of questions for what they are. So how is this one different from the other ones? In a couple of ways you might see it differently. I don't know. As far as I know, there's not really an identity that's going to work. But remember, it's all about isolating. Like that's really what we were doing with the quadratic formula, solving by factoring. What we're doing is resolving the fact that I've got x squared and x, and I can't put them together. They're not like terms. But if I can turn it into two individual x's and use the zero product property, I can do that. So what if I common factor this? I can common factor this, and I get the sine on its own, and I get the cosine on its own. We'll do that. We'll get to that, and we'll show you what it's like. But that's a totally different way of managing the fact that I've got sines and coses all mixed up. And there's nothing that I can do about that in the form that it's in. So all four of these are slightly different, and you want to recognize them. So I would even say after we're done all four of the examples, you could look at their solution and come back and sort of look at them all together in one place on a page at the same time and kind of try to come to terms with their different characteristics and what jumps out at them. Why would I solve this one this way? Why would I solve that one that way? How am I going to figure all those out? Okay, so let's dive into this. That's enough talk. Notice that it's 0 less than or equal to x less than or equal to 2 pi. Okay, so again, there's going to be multiple answers to lots of these. So we talk. This one's kind of like your straightforward quadratic trig equation. I'm just going to factor it. Again, it kind of, you could think of it like this. A squared minus 2a minus 3. How do I factor that? Go ahead and try. Like you could even factor, get some scrap paper and replace all the sine squares x's or sine x's or cos x's or whatever it is, replace them all, right? And do it that way. So this is going to be sine x minus 3 and sine x plus 1. If you expand that, you'll get the line above it. Zero product property, therefore, we'll do it the long way. Once sine x minus 3 is 0, or sine x plus 1 is 0, which means for this one, sine x is 3. And then here's the thing. Everything we've done, trig in grade 11, and then into grade 12, unit 6 for us, and so far in unit 7, like everything. You need all those skills in order to solve these. Because if it's just a sine, it's relatively easy, but what if it's a secant? Then you got to use reciprocals, and you got to think of angles and standard position. What if it was like a secant 2x? Then you got to be able to think, like there's a lot going on in some of these questions. You could build one question that would test almost everything in these units. It's kind of interesting to think of it that way. That wouldn't be my intention to give you like the hardest question possibly can see, but just keep in mind that all of that stuff, even identities, comes into play here. So if sine x is 3, when is sine x equal to 3? Hunter? Never. So this part's not possible. I like to say not possible there because if you say no solution, that's kind of not true. There is a solution, but it comes from the other part. I don't know that that means you're wrong if you say that, but I just like to say, okay, this part's not possible, but I'm going to have a solution from over here. When is sine x equal to -1? When x equals 3 pi over 2. I just got that from the graph, right? But angles of standard position, however you like to do it, get that answer. It says solve each of the following to 2 decimal places, but I will qualify this. If you can do an exact answer, you have to. And that'll go for the test. Well, we'll talk a little bit more about this, I guess, maybe down the road, but challenge yourself that if you can do an exact value, that would be the expectation. 2 decimal places if necessary. And in some cases, it will be necessary. Okay, but we should be able to recognize when it is, when it isn't. And that's it. I only have the one. There's no other possible answers. So that guy's done. Let's try the next one. So remember, I can't factor it the way that it is. I can't get secant by itself and tan by itself. Like there's nothing that I can do to resolve that. So I recognize that secant squared x is one of the identities. That's a useful one in this case, which is 1 plus tan squared x. It's not a common one per se, and it probably wouldn't come up that often in your homework. Hopefully it's more ones that you recognize quickly. So now again, this isn't quite finished yet. I got to kind of expand here. So that's 2 times 1 is 2 plus 2 tan squared x minus 5 tan x minus 5. So 2 tan squared x minus 5 tan x minus 3 equals 0. And again, maybe I start thinking about this as like 2a squared minus 5a minus 3. So complex trinomial, why don't you try to factor that? I got 2 tan x plus 1 and tan x minus 3. Anybody else get that? Okay, that means tan x is equal to -1/2 Don't get confused at that step. That's easy, right? I just move the 1 over, like 2 tan x plus 1 equals 0. Move the 1 over divided by 2. If you don't like that, ask me about it after. I'll show you slower. Or tan x equals 3. Now we have to do some thinking here. Anybody help me out with some thoughts? Okay, when is tan x equal to negative a half? What do you think? Come on, folks. This is like you have to be able to do it. Don't just sit there and wait for me. So think about it for yourself. See what you can come up with. Why would you use that? Not special triangles. Why would you use that? Okay. Zoe? Right. Special triangles is a great idea. And this question looks like it's specifically designed to fool you into thinking like sine of x is 1/2. I'm good. Cos of x is 1/2. I'm good. I can use special. Tan, it doesn't work. So we need to know when we can use special triangles, when we can't. So like I was just saying before, if you can use special triangles, that's the right thing to do. At first glance, you would think you could here. Turns out you can't. So like Alex said, you're going to go shift tan positive a half. A lot of people are coming to me and it sounds like they're putting a negative into the calculator. We never put negatives into the calculator when it comes to trigonometry because the answer that it gives is not necessarily clear what it's telling you. But if I use my understanding of related angles, I can kind of do everything myself. So it's like I'm going to find the related angle of x, which works out to I'm in the wrong mode here. Setup 4. Shift tan 0.5 gives me 0.464. I'm going to keep it's supposed to, I think it said, what did it say, 2 decimal places? But I'm going to keep an extra 1 just for now. Okay. But tan is negative in the second and fourth quadrants. So I'm going to do pi minus that and 2 pi minus that to get the answer. And I probably wouldn't show this work at this point, even on a test. So I'll show it here just so that when we're looking at it, we don't get confused about where the answer came from. And x equals 2 pi minus. And I think it works out to 2.68 and 5.82. Let me know if that's not right. And what about tan x equal to 3? So when it was sine x equal to 3, it's not possible. Is that also true here? Visualize the graph of tan in your mind. Does tan hit 3? It does, because it's different from the other ones. It's not bounded like that. So, so let's find where it's equal to 3. So x is equal to, it's positive. So I'm just going to go shift tan, and I get 1.25. And then I can add pi to that because it's also, that's going to be my first quadrant. Add pi to that. And so pi plus 1.25. And that should give me 4.39. And I'm just going to summarize here. So x is 1.25, 2.68, 4.39, and 5.82. 4 answers for a different reason from why we were getting like 4 answers previously in the other stuff we were doing last week, right? Different reason, because of it being a quadratic trig equation. Yep.
Does it matter which order you put the answers
No. But like if you want to help me while I'm marking, you put them in the right order. You put them in like smallest to biggest just so that it's easier to read, right? But no, you're not going to lose marks because of that. If your solution is super clear, you don't need to rewrite. Everybody's a little bit different. But if you have any doubt, it's kind of nice to rewrite it. Make sure you've got all four. It helps you as well, I think. Any other questions? Okay, let's try a couple more. Do you remember what our plan was for this one? Cos 2x, sine squared x, sine x. I can't have all these different things in it at the same time. I have to be able to either common factor or like trinomial factor, complex trinomial factor, difference of squares factor, something along those lines. Daniel, what do you think? Yeah, the other thing is, it's not going to work if my angles are different. So even if that was like sine 2x, that's different from 2 sine x. Those are not the same thing, and we can't start adding those things together. They're not like terms, you can't add them together. So even if it was sine 2x, there would still be a problem that would have to work out before I could do that, right? Something to think about. So this one works out to 1 minus 2 sine squared x plus 3 sine squared x plus 2 sine x equals 0. 3 sine squared x minus 2 sine squared x is sine squared x plus 2 sine x plus 1 equals 0. So this is a squared plus 2a plus 1. So it's an easy one, sine x plus 1, all squared, sine x plus 1, same thing. From here on down, if we've kept up with everything, we're awesome. It's easy. What would the graph look like? That's a good question. Maybe we'll do the next example and then pull it up and see afterwards. What am I doing here? Therefore, sine x equals -1. We already saw that. So x is 3 pi over 2. This one only has one solution. This happens too. The last unit, we were talking about this before. So unit 9 is combinations of functions. So what happens when you start adding functions together like cosine plus sine or cosine times sine? What would that look like? Kind of interesting. So we'll learn a little bit more about that at the very end of this course, about what happens when you have different things together. But and it would be interesting to revisit and look, after we've done a little bit of that work, look at a question like that and think about what the graph is. But I think it'd probably be pretty complex. Okay, let's do this last one. If you didn't practice this and get to a point where you're comfortable and you're starting to understand that there's different methods, if you saw all 4 of those questions on a page, it would be very overwhelming to try to figure out what to do because they're all very different. You gotta kind of take the right approach, and if you try to solve one with the wrong method, it's just not going to work, right? So it's really important that you spend a little bit of time thinking about each question, the way it's presented, and how you would tell how you're going to solve it. And part of that is when you're good enough to sort of abstractly notice that sine x is like an A, cos x is like a B, and just think of it that way. And then you notice that this one has a common factor in it. So I can do sine x, and then it's cos x plus 2 equals 0. And it turns out it's pretty easy to solve. But if you didn't notice that, I don't know what else you could possibly do. So people start to try to guess and check. Yeah, good luck. Or move something to the other side, bad idea. Right? Not going to help you. You got to practice these and kind of know the different traits and the different ways of doing it. So that means, therefore, sine x equals 0 or cos x equals -2. Well, again, this is not possible. Where is sine x equal to 0 within our given domain? Alex? Very nice. I think this came up on a test this year, so maybe you've already thought about that. But this one just happens to have 3 answers in our typical domain that work. So again, it's all about, there's no one method, one formula that's going to work for this stuff. You really pulls together a lot of things, and I think that's why people do find this in particular to be quite challenging. There'll probably be 3 or 4 of these on the test, and they're going to be all kind of different types. And maybe one of them won't even look exactly like anything. There's nothing else, some other magical system that I haven't shown you. There's not anything else, at least not that I'm aware of. But there will be questions that could look a little bit different. What if I even gave you the question, sine x cos x equals -2 sine x? You would have to move it all, set one side equal to 0. That's something that you would certainly have to think about. I might not give them all to you as equal to 0 in the beginning. You might have to rearrange a little bit or something like that. Okay? If you could common factor out a number and divide both sides and kind of simplify it, get rid of it, like all those strategies are useful. Any questions? Practicing all of this is really good practice for everything else, all the other angles in standard position, all the other stuff that we've been doing. So if you work through these and you've done all the identity stuff, you're probably already pretty prepared for the test, even before worrying about the review and that kind of thing. Keep that in mind. I think it's set to be posted tomorrow morning.